Okay. Good afternoon, everyone. Thanks for giving me the opportunity to be here. So I'm going to stay in Europe, in the Pyrenees. You are more familiar probably with the Asian seismotectonic setting, but this is a very close place to visit between Spain, Andorra, and France. And I'm going to focus also on geomorphologists, tectonic geomorphologists. I'm going to focus on the uppermost part of the lithosphere, that is the landscape, that we've been using to constrain the activity of several faults in the Pyrenees. So the work I will present is, well, there are more people involved than the ones you see here, but I want to highlight that often I work with people from the others. Well, Pierre Lacan, that is based now in Mexico, but developed his PhD in the Pyrenees, and also Marc Viaplana-Musas, that is in Barcelona and is also close collaborator. So the Pyrenees, this is the classical seismic profile sections, showing that the Pyrenees is an alpine orogen that was built as the inversion of a rift, a historic rift. But since since 40 million years ago, this convergence finished, and we started a quiescence period followed by the neotectonic period. Present day, so if we look at the seismicity, we can see that, well, this is only seismicity from the last 20, 30 years. But most of the focal mechanisms are telling us that we are in an extensional context, except for some parts, the western and eastern terminations of the range, where we also find a strike slip mechanism. And you can see here a figure, synthetic figure with the seismicity, also showing the historical seismicity. So in this case, it's like Ricardo was saying, if we could travel to the past, so here in the historical times, if we were in the Middle Ages, we will be very unlucky because almost 1,000 people died in each of these earthquakes, like the Camprodon earthquake in 1428, or the Ribagorza earthquake, 1373. That was the focus of my PhD. So my mission was finding the seismogenic source of this earthquake in the middle of the Pyrenees. This one with a large uncertainty in the epicentral area, and the Biela earthquake, it was a 5.2 earthquake. Okay, so first, well, I'm gonna highlight these points. We are in a place with faults are really slow. At present, during the neotectonic period, well, it's not well constrained, but it seems that extension prevails. Slip rates of the faults are way smaller than 2 millimeters per year. These are the ones that I constrained for the fault I studied in my PhD. And that means interseismic times of way larger than 10 kiloyears for these morphogenic earthquakes. What about the geodetic data? Right now, it's not time to validate this data. Maybe in 10 years, or we start having significant data. But now we can say that we cannot tell if there is uplift, but in any case, it's much slower than in the Alps. So. Okay, so this being said, we have to remember also that the faults that we are studying, we don't know if they broke in these historical earthquakes. There's not enough record in Middle Ages, but most of the faults that we have in the Pyrenees, for sure, didn't break during the historical times. So it's not part of our history in the way that people is not aware of this. No, it's not a part of our prevention. During the last decades, in Spain and Portugal, we did a large effort of compiling this database of studied faults. Probably here you don't see that, but we will zoom it. I get profit of this figure to announce the two posters of my colleagues that are in the hall in different areas, the Betics and the Catalan coastal ranges. Okay, let's look to the map of faults in France. That is at some point will become also an official database, I hope. You can see here how the faults in the Pyrenees can be distinguished in two groups. The faults that follow the alpine trend and these other faults that are part of this western extension system that we've been talking also yesterday. And you can see here the Cerdaña-Conflans fault, that fault also, and other faults in the area that respond to this opening of the Mediterranean, and that also explain the activity of these active faults that we have in the Catalan coastal ranges. This will be the fault that Cerdaña fault. And you see how close it is from this 1428 earthquake, but we know already that it was not sourced here. It was not. So now the source of this earthquake still is unknown. But we have other faults like this Amer fault that was producing these two earthquakes. You see how close in time it's considered a trigger series, and that follow this Ribagorza earthquake. So here is my connection point with Tapponnier, because, well, this was the first paper before starting my PhD that my advisor asked me to read, and it was written by Anne Brier, that I met today personally, and that described this Cerdaña-Conflans fault, which has really nice triangular facets. So it was studied from different points of view, and it's been also discussed about if it's a fossil landscape or it is not. But you will see that it's a very evident structure in the models and in the field. So here you see the triangular facets dissected by glacial valleys, and in the downstream wall covered by neogene and also quaternary deposits. In the model, in the elevation models, you can see how clear the fault is here, also here. This is also the Cap Sir fault, really straight, the Serre. So we have this bunch of faults that I've not been studying in detail. But in the 2 years ago, we published the results of a temporal seismic extension set network. And we saw that many of the small earthquakes that we have today, some of them between 3, 3.5, even 4, are not aligned with this main trend, but are being nucleated in the massives that are being uplifted and accommodate these stresses. But let's go to the area where I focus in the last years, that is the Central Pyrenees, and also the area that Pierre Lacan studied in his PhD, that are part of a system that results from the reactivation of a main thrust that separates Iberia from Eurasia, let's say. That is the Gavarnie-Lacour-Ochot thrust. That was one of these inverted thrust during the Alpine times, that now is acting as a normal fault. How we characterize this fault? Well, you will see that triangular facets in this is a picture of the Maladeta area. So this system is called Maladeta, North Maladeta, Bedou, that is the westernmost fault, but it's composed of this set of echelon faults. And that present this aspect. So it's really hard, it's really challenging, because the area here is sculpted, is eroded by the glaciers. and has a really energetic process shaping the landscape. We don't have we have some faults similar to the one not strike slip but normal faults in the glacial cirques. But the large faults, so you see they are kind of difficult to follow. Maybe here in the Google Earth view you can follow it a little better. And with the LiDAR images also, we see the fault is going this way. But the fact is that at the bottom of the valleys, glacial valleys, we don't see any ruptures, any evident scarps affecting late quaternary, not late quaternary, but post-glacial deposits. However, if we consider the envelopes of these old markers, that I'm going to show you a little how we studied them, we can trace them and even quantify offsets that go up to 700 meters and that are continuous along 70 kilometers. Okay, I will go back to these old markers, but just a quick mention to, well, there were two earthquakes in 2023 at the Neve fault. That is a little, I don't remember if it was Neve fault or Peira Sorda fault. And then the Coronas fault earthquake that was quite well felt in the area, and that motivated the set of a temporal seismic network around here, and that was produced by this Coronas fault that could be considered a secondary fault of this large system. Let's look to the aspect of this fault. This fault is affecting and displacing the Aneto Massif. Aneto is the highest peak of the Pyrenees. And I traced this fault along 12 kilometers, accumulating displacements up to 150 meters. In the field, at some parts, the scarp is quite clear, quite neat. And we can even see the striation grooves along the fault that, of course, could be inherited from former activity during the Alpine period. But we are now, there's a work in progress. We try to date the scarp. This is a 50-meter scarp that was sampled for cosmogenic isotopes. And at least we are also waiting for results because I have like 9 samples, but I only got the edges of the base of the scarp. And also we tried this other exposure dating method. Well, these are samples of beryllium-10. And also we tried the Smith-Hammer method of exposure dating with Matt Tompkins that developed his PhD here, calibrating the values with the granites in the glacial landscape. Okay, so this is our work in progress. But let's go back to these large offsets that we assign to this fault. So the fault will be here. This is a triangular isolated facet, so dissected by the glacial valleys. And I was very lucky because in my PhD, there were Miocene sediments at the toe of the fault. So in the inner part of the range, we don't find any Miocene sediments. All is like basement, really from Paleozoic times. But one of the few places where you can find Miocene sediments is here in the Predo plains. So these sediments, I could study them and study the fossil content in seeds and pollen and constrain the age of the onset of the fault activity, which allowed us to constrain the slip rate of this fault using these old markers that are the low relief topography, but also to find that these seeds were giving us paleo altitudes 1,000 meters below the present day altitudes. So even if it's really low, is the only, well, in this area is the only uplift rate that we have so far. Okay, so just I'm going to dedicate a few minutes to explain you what we understand by this low relief topography that it's all around the planet, and is still preserved in many mountain ranges in the highest part. Okay, so well, as you can see, these flat mountains are all around the world. In the Pyrenees, they were described by different geographers and geologists during the beginning of the century. Also in the Alps, it was called the fundamental surface. And our vision is that at some points, these are pictures from the Pyrenees, they are really flat surfaces, but at other places, these reliefs, you cannot produce a flat relief at this height, and it's the remnant, they are the remnants of a low relief, but that still can have like 250 meters, 300-meter relief. So it's not completely horizontal, or it can have more than 20 degrees slope, for instance. And regarding this, Oli and Pei, they were saying that they are not folded mountains. Well, maybe they are, but in the way that most of the mountains we study, they are developed and flat at the top, because in the high parts is where the erosive process, the quaternary incision, has not reached yet. So you can have the preservation of these patches, these remnants, but if you are lucky and the quaternary erosion didn't eat all these surfaces, you can have surfaces that are not really flat, okay? So this will be the case during steady-state landscape quiescence periods, for instance, in the Pyrenees, where the uplift rate is equivalent to erosion, and the rivers are like weakened. So they don't have enough energy to dissect this old landscape, and without this incision, the landscape just with mass movements, and it becomes smooth. Then when you have a reactivation of the structures, or either also a large drop in the base level, you have the rivers, let's say, destroying this old landscape. So here you have more examples. You can play with Google Earth and find many patches of these surfaces all around, like sometimes excavated by the glaciers. And also, often we find the paths of old drainages, very nice ones, following, for instance, longitudinal trends instead of transversal to the range, which is now the common path of the rivers. Like most of the rivers are like that, but at some points we find these paleo valleys that follow the trend. So we studied these surfaces with a systematic method, analyzing the digital elevation models, and we map all the surfaces over 1,200 meters. We erase all the structural surfaces to avoid, even if they are part of the old landscape, we wanted to avoid this, let's say, bias, because sometimes you can generate a structural surface without being an old landscape. And we did it using the local relief that is very simple. Assigning to every pixel in the model a difference between the maximum and the minimum height that you find in a pixel window, in this case of 500 meters. So we erased all the places with local relief larger than 250 meters, and we obtained this map of patches of low relief topography within the Pyrenees. It was not the first time that these surfaces were studied. So even in my PhD, I was studying them, but not with this method, but using just the slope. So it was like more restrictive. Okay, when we have these patches and we obtain the topographic sections, only considering the patches, we can see how systematically, when we cross this structure of normal eta fault, the Midi-Bigorre fault, these envelopes are displaced, and that's how we quantify them, quantify the offset. And this means that, these faults have been active since the onset of the system at the end of the Miocene. How these faults control the landscape? So you see here, so this is the North Malaita fault. Here we have the north, and here the south. This is France. And this is the main divide of the Pyrenean range. What we propose is that the onset of this system, it's related with a drastic jump in the main divide that probably was located at this part. So it would be here without the activity of this fault. Of course, this divide is migrating because the northern side of the range has a larger slope than the southern flank, but still this migration was accelerated by the onset of these faults. Independent evidence of this location of the paleo drainage divide are derived in these studies, where they found as a number of evidence telling that the conglomerates that were feeding these alluvial fans that are not evident now during the Oligocene were sourced around the area of the North Pyrenean zone. So more or less this will be the scheme, and this will be the main divide right now. This means, well, this will be one of the, it's funny because I found that postcard, and you can see here a wind gap of this drainage, let's say, of these valleys, paleo valleys, that are now cutting the main divide. So the model that we propose is that the postorogenic shape of the Pyrenees had the paleo divide really close to Aquitaine basin, and then after the onset of this, the activity of this fault, due to probably outer extension driven by enhanced exhumation here, so activated these faults. Another evidence, you can see here one of the most beautiful mega alluvial fans probably in the world, the Lanemazan fan, that started in early Miocene, probably because all this area was suddenly available as a source area to these Garonne and Nest valleys. So this will be related to the onset of this activity. So just a quick mention to the models. I'm not expert in these models, but I can think of a compensation of the erosion, also related with deep processes that make that the high mountain status is guaranteed, and every time you have a low relief, then you have this compensation in a kind of a breeze. This has implication. I think implications have to be more taken into account than it's been until today in models like thermal histories, exhumation models in the Pyrenees that really don't look at the active faults, because it has an impact. And other possible models or processes that could be taking part are very variable, from a loss of the slab, erosional rebound, lithospheric flexure. In any case, I finish with some final remarks. We have to take in account that, basically that the active faults control the landscape, the development of the landscape, and that we have to consider that at any moment we can have a larger than six magnitude earthquake. So I wonder if you know what to do if we have one of these now. Thank you.